Let's check if I'm online. Yes, I am. All right, great. So as you can see, here, a new language model was released by this company called DeepSeek. I haven't read this paper yet. I'm very interested to see what they propose, to see how reasonable the results are. They open sourced everything on Hugging Face as well. So we might play around with it. We'll see if there are any spaces up on Hugging Face to see what it can do, what it can't do. But yeah, I just kind of have this open. I am quite interested in seeing and just going through the paper. Like I said, I haven't gone through it, so this will be a very active approach in kind of reading this paper. I won't be necessarily presenting this paper as though I have read it already. I will be kind of reading this paper actively. I'll be kind of taking notes here on the side. And I think this will actually be a really interesting way of going through how we can read papers together kind of in this Twitch-like environment. So I'm just trying something new. I think this will be kind of fun. Let me just settle in here. Let's get some music going. Let me just take a quick sip. Got to stay hydrated. Sippy cup. Let's go. Let's get some music going. Let's just settle in. I have one viewer. How's that one viewer doing? Hope you're doing well. Hope you're staying hydrated. I got a sippy cup. So you know I'm staying hydrated with the sippy cup. All right, so let's begin. So let's pull up the highlighter here. So DeepSeekMath, this paper is called DeepSeekMath, Pushing the Limits of Mathematical Reasoning in Open Language Models. So let's see. Mathematical reasoning poses a significant challenge for language models due to its complex and structured nature. In this paper, we introduce DeepSeekMath 7 billion, which continues the pre-training of DeepSeek Coder Base v1.57 billion, which is a prior model that they've released. I saw this on their GitHub. This was for this is just a code completion language model, 7 billion parameters, with 120 billion math-related tokens sourced from the Common Crawl, together with natural language and code data. So this is going to be quite interesting. I'm kind of new to this tablet, so just bear with me here. Goodness. All right, DeepSeekMath 7B has achieved an impressive score of 51.7 on the competition level math benchmark without relying on external toolkits and voting techniques, approaching the performance level of Gemini Ultra and GPT-4. Now, if only we knew how big Gemini Ultra and GPT-4 are. Obviously, there are leaks, at least surrounding GPT-4, it being a mixture of experts model. But who knows how accurate that is? It might be accurate. I don't know. But good luck trying to figure out what Gemini Ultra is. What we do know is that it is it is a model trained on data, which is so insightful. Self-consistency over 64 samples from DeepSeekMath 7 billion achieved 60.9% on math. Now, I don't know what self-consistency is. So perhaps we'll look into this. I'm sure they reference other papers that introduce this. I've never heard of this. I'm sure it's common in large language model trainings. So we'll read into this as well. So actually, I'll just make a note here before I forget. Okay, hold on. So here, we'll just put a little star here, call this 1, and then bring it over here. Self-consistency. What is it? Question mark. Okay. Over 64 samples, and then first we harness the significant potential of publicly available web data through a meticulously engineered data selection pipeline. Second, we introduce group relative policy optimization, a variant of proximal policy optimization that enhances mathematical reason abilities while concurrently optimizing the memory usage of PPO. So I assume that by, let's click this, I assume that by group relative, maybe they kind of batch these things, do it all in parallel. I'm just guessing. But again, this will also be very interesting to read about. So they call this GRPO. Okay, cool. And here we have this figure, top one, accuracy of open source models with this math benchmark over time. And as you can see, DeepSeekMath is really approaching GPT-4 and Gemini Ultra, and has actually outperformed the GPT-4 early version. Cool. So, large language models have revolutionized the approach to mathematical reasoning in artificial intelligence, spurring significant advancements in both the quantitative reasoning benchmark, the geometry reasoning benchmark, and the geometry reasoning benchmark. Moreover, these models have proven instrumental in assisting humans in solving complex mathematical problems. I assume Tau 2023 is the, oh my god, what's that Google paper called? Was that the alpha geometry? Geometry? Is that what it's called? Is it Tau? Is it Tau at all? Was it from Tau? No, it's not. Oh my god. Wait, which one is this then? Okay, anyways. However, cutting-edge models such as GPT-4 and Gemini Ultra are not publicly available, and the currently accessible open-source models considerably trail behind in performance. So in this study, we introduced DeepSeekMath, a domain-specific language model that significantly outperforms the mathematical capabilities of open-source models and approaches the performance level of GPT-4 on academic benchmarks. To achieve this, we create the DeepSeekMath corpus. This is, which is very nice. Thank you for creating a corpus, a large-scale, high-quality pre-training corpus comprising of 100 billion math tokens. It's extracted from Common Crawl. Let me straighten this out. It is extracted from Common Crawl using a fast text-based classifier. In the initial iteration, the classifier is trained using instances from Open Web Math as positive examples, while incorporating a diverse selection of other web pages to serve as negative examples. I see. Subsequently, we employ the classifier to mine additional positive instances from the Common Crawl, which are further refined through human annotation. Okay. Nothing too crazy here. The classifier is then updated with this enhanced data set to improve its performance. Okay, cool. The evaluation results indicate that the large-scale corpus is of high quality as our base model, which they're going to be talking about DeepSeekMath base 7 billion. I'll just kind of be referring to this as DeepSeekMath. Achieved 64.2 on GSM 8K. And 36.2 on the competition level math data set, outperforming Minerva 540B. This is a 540 billion parameter model? I've actually, wait, what? Minerva 5. Is this really a 540 billion parameter? Oh, it's from Google. That's why. I was about to say, that's huge, dude. Solving quantitative reasoning problems with language models. We present Minerva, a language model capable of solving mathematical and scientific. When was this released? Uh, 2022. Really? Oh, maybe. Actually, maybe I've seen this before. Perhaps. But yeah, 540 billion parameters is absolutely insane. Anyways, where were we? Minerva. Outperforming Minerva 540B. In addition, the DeepSeekMath corpus is multilingual, so we notice an improvement in Chinese mathematical benchmarks. We believe that our experience in mathematical data processing is a starting point for the research community, and there is significant room to improve in the future. Okay, cool. So far so good. DeepSeekMath is initialized with the DeepSeek coder base. So, interesting. This is very interesting. So the DeepSeekMath base is actually just the DeepSeek coder fine-tuned. As we notice that starting from a code training model is a better choice compared to a general LLM. This isn't too surprising. Furthermore, we observe that the math training also improves model capability on MMLU and BBH benchmarks, indicating not only does it enhance the model's mathematical abilities, but also amplifies general reasoning capabilities. Dubious claim, but okay. After pre-training, we apply mathematical instruction tuning to the DeepSeek math base with chain of thought, program of thought, and tool-integrated reasoning data. The resulting model, DeepSeek Math Instruct 7 billion, beats all 7 billion parameter counterparts and is comparable with 70 billion open source instruction tuned models. All right, let's see. Furthermore, we introduce group relative policy optimization as a variant reinforcement learning algorithm of proximal policy optimization. So before we begin, proximal policy optimization. I really would like to go through this paper as well. This was from OpenAI. Yeah, so perhaps we should go through this at some point, actor-critic style. So the core algorithm, run the policy in an environment and then compute advantage estimates. How do they define advantage estimates? As this very long equation that I don't know of. Okay, so I mean, I could probably spend another day or so on this paper, but let's see. So GRPO foregoes the critic model, instead estimating the baseline from group scores, significantly reducing the training resources. So it foregoes the critic model. I see. By solely using a subset of English instruction tuning data, GRPO obtains a substantial improvement over the strong DeepSeek Math Instruct, including both in-domain and out-of-domain mathematical tasks, and they show kind of the improvement during the reinforcement learning phase. We also provide a unified paradigm to understand the different methods, such as rejection, sampling, fine-tuning, direct preference optimization, which a lot of people have been raving about recently, PPO, and GRPO. Based on such a unified paradigm, we find that all these methods are conceptualized as either direct or simplified reinforcement learning techniques. Yeah. We also conduct extensive experiments, online versus offline training, outcome versus process supervision, single-turn iterative reinforcement learning, and so on, to deeply investigate the essential elements of this paradigm. At last, we explain why our reinforcement learning boosts the performance of the instruction-tuned models and further summarizes potential directions to achieve a more effective reinforcement learning based on this unified paradigm. Okay, cool. So let's go to the core contributions. So their core contributions include the scalable math pre-training, along with the exploration and analysis of reinforcement learning. So first is the math pre-training at scale. Our research provides, let me highlight this. Our research provides compelling evidence that the publicly accessible Common Crawl data contains valuable information for mathematical purpose. This I believe 100%. By implementing a meticulously designed data selection pipeline, we successfully construct the DeepSeekMath corpus, a high-quality data set of 120 billion tokens. Okay, yeah, they mentioned this. Our pre-trained base model achieves comparable performance with Minerva, indicating the number of parameters is not the only key factor, in mathematical reasoning capability. A smaller model pre-trained on higher quality data could achieve small performances. I mean, yeah, it can. Of course it can. We share our findings from math training experiments. Code training prior to math training improves model's ability to solve mathematical problems, both with and without tool use. This offers a partial answer to the long-standing question, does code training improve reasoning abilities? Okay. Partial. Now, I do like this idea of taking a model trained on code and then kind of going over to math, kind of training a language model on math tokens specifically. I like this idea because there are quite a few parallels in that you have, say in math, you have certain axioms and then you kind of build up. I mean, with code, it more or less is the same thing. You have you have a handful of instructions that you can operate within, and then from there you build up to more complicated things. So I do think that this is a natural extension. If you want to improve in mathematics and you have to choose between a general language model and maybe a language model trained on code, the code does make sense. But I don't understand why this question, this does seem to be a prescient question in the field, which I'm quite confused about. In all honesty, I'm very confused about, because like, who cares? Just build a different model. Like, spend the time to work on a different model to try to reason through things. Start with the data, start with benchmarks for reasoning, beyond the text-based reasoning. It's a good first start, but I think this question, if we have a whole field or like a whole team, a whole niche dedicated to this question, I think it is a bit, I think we are missing the forest for the trees, as the expression goes. So it's an interesting question, but I don't know. I think there are better ways to formulate questions and work towards how do we improve towards reasoning abilities. I think part of that might be like a search-based approach, but again, I'm thinking out loud here. So we believe it does, at least for mathematical reasoning. Okay. Sure. Although training on archive papers is common, especially in many math-related papers, it brings no notable improvements on all mathematical benchmarks adopted in this paper. They also provide exploration and analysis of reinforcement learning. Okay. We introduced the GRPO, an efficient and effective reinforcement learning algorithm. GRPO forgoes the critic model instead of estimating the baseline from group scores, significantly reducing training resources compared to PPO. We demonstrate that GRPO significantly enhances the performance of our instruction-tuned model by solely using instruction tuning data. Furthermore, we observe enhancements in the out-of-domain performance during the reinforcement learning process. And then they also provide a unified paradigm to understand the different methods. We also conduct extensive experiments, which, yeah, they mentioned. Based on our unified paradigm, we explored the reasons behind the effectiveness of reinforcement learning, and then summarize potential directions. Okay, so this is more or less the same thing that we have already read. And then they have also claimed that English and Chinese mathematical reasoning has improved because they have multilingual tokens. Formal mathematics. And then they have the summary of evaluations, formal mathematics, NLU, reasoning, and code. Okay, so then let's just get to it. Math pre-training. So I'm very interested to see how they crawled for data. So let's discuss this. Before that, let me just lower this. Should I switch it? I mean, I'm kind of vibing with this. It's cool. I'm vibing with Ratatat. Whose water bottle is that? This is my water bottle. This is my Nescafe has adult sippy cups. This is mine. It's refreshing. Yo, it doesn't spill. Look. Dude, it's an adult sippy cup. Look at that. No spill. Look at that. No spill. Absolutely no spill. No spill. All right. I don't know why you're getting so upset in chat. I'm just drinking water. It will spill if you keep doing it? No, it won't. Technology, baby. All right, back to the paper. So, let's discuss math pre-training. So, first they have to collect data from Common Crawl, and then what they call decontamination. Decontamination. In this section, we will outline the process of constructing the corpus from Common Crawl. As depicted in Figure 2, we present an iterative pipeline that demonstrates how to systematically gather large-scale mathematical corpus from Common Crawl, starting with the seed corpus, a small but high-quality collection of math-related dataset. It is worth noting that this approach is also applicable to other domains, such as coding. Now, this I believe because I wrote a paper on this too regarding, regarding speech data, how you can acquire and improve your speech corpus with a speech enhancement model. I'll be presenting that at ICAST 2024 in Korea. So yes, this iterative process I do believe in. So before we continue, let's check out this figure. Okay. Let's see. So you start with the seed data, train a fast text model. This is the classifier. Recall math-related web pages from Common Crawl. And then you get more data. And then you discover math-related domains. I do not know what they mean by this. We'll see. Annotate math-related URL path from labeler. So this is the human in the loop. And then deduplicated. And then they have a deduplicating process here between 2 and 4. And then all this data then gets added to the seed, and then they repeat it. First, we choose OpenWebMath, a collection of high-quality mathematical web texts, as our initial seed corpus. Using this corpus, we train a fast text model to recall more OpenWebMath-like mathematical web pages. Specifically, we randomly select 500,000 data points from the seed corpus as positive training examples, and another 500,000 web pages as from Common Crawl as negative ones. So I guess they're just doing classification on web pages. So they'll use this. Let's go to the pen for a sec. So they'll start with this data. They'll random sample 500,000. And then also from, let's say Common Crawl is over here, they randomly take another 500K, and then they just assign labels to it. So they say, hey, this is good data, we'll call this 1. This is bad data, we'll call this 0. And I guess you just run a classifier on the 1 million examples. And then once you have this classifier, you then classify based on more data. and then add the data to your corpus, which I guess is the discover math related domains. We'll see what they mean by this. And then they have human labelers, and then they do the deduplication, and then I guess they repeat. Okay, that's not too crazy. We employ an open source library, fasttext.cc, if you guys want to check that out. For training, configuring the vector dimension to 256, the learning rate to 0.01, maximum length of the word n-gram to 3, and then the minimum number of word occurrences to 3, and the number of training epochs to 3. To reduce the size of the original common crawl, we employ a URL-based deduplication and near deduplication techniques, resulting in 40 billion HTML web pages. We then recall mathematical web pages from deduplicated common crawl with the fast text model. To filter out low-quality mathematical content, we rank the collected pages according to their scores predicted by the fast text model, and only preserve the top-ranking ones. Here we go. Okay, cool. This is very cool. So maybe this is very much like an active learning type approach. In active learning, so let's go over here, right? So in active learning, you'll have this classifier, and you have just all of this data. Actually, we gotta do the cylinder for data, man. It's a database, bro. So you have your database, and there are no labels, so you don't know what the labels are. But if you have a classifier to kind of classify this data, what you do for active learning is ideally this classifier will go through all the examples in your database and then provide to you labels, right? So you'll have all your labels. Now obviously, because it's a classifier that you trained, you know that it's not going to be perfect. What is done in active learning is say, well, I want this classifier to iteratively improve. So instead of getting the labels, what I'll do is I'll actually get, and we'll just say for simplicity's sake, we'll just say that I want, as opposed to the labels, I actually want the probabilities, the class probabilities. So, and we'll assume that this is a binary classification, so you only have 2 probabilities. So you'll have the probabilities of each class here. And then what you can do is, let's say for this sample you have 0.3, 0.7, okay? For all of your examples, you can measure the certainty of your prediction by using something like entropy. For example, if it is, eraser. So if you have 0.5, 0.5, you have high entropy. This is in the binary case, this is the most uncertain your classifier can be. So what you'll do is you'll actually take this sample, feed it to a human labeler. The human will do the annotation, and then that goes into your training data, which then retrains your classifier. So essentially what you do is you'll get all the most uncertain examples, have it labeled by a human, put it in your train set, retrain the classifier, and then go back to the database that you want labeled. And this is kind of how active learning is done. Now, Now in this case, they're kind of doing the opposite, right? So let's see. Can I even select? Oh, I can't. Let me just select all of this, Control C, Control V. So what they're doing now in this case is saying, well, as opposed to getting, they're kind of like flipping the inverse. They're kind of flipping the active learning and saying, well, we want the highest quality data immediately, so we will actually get the most certain. So, 0.99. Okay, this is like the most certain prediction, and we will preserve these. So we'll actually get all of these, and then just immediately put it back into the training corpus. And then where does the human in the loop come in again? So we preserve the top ranking ones, so kind of the most certain. I assume it's the most certain based off some certainty measurement. The volume of data is preserved, and then let's see, where do they mention the... Okay, let's continue. The volume of data preserved is assessed through pre-training experiments on the 40 billion, 8 billion, 120 billion, and 160 billion tokens. For the first iteration, we choose to keep the top 40 billion tokens. That's a lot of tokens. After the first iteration of data collection, numerous mathematical web pages remain uncollected, mainly because the fast text model is trained on a set of positive examples that lack sufficient diversity. Therefore, we identify additional mathematical web sources to enrich the seed corpus such that we can optimize the fast text model. First, we organize the entire Common Crawl into disjoint domains. A domain is defined as web pages sharing the same base URL. Okay. So that's what they mean by math-related domains. See, this is why you read. When I saw this, I thought they were somehow gonna figure out like, oh, this website or these tokens are related to like signal processing. This is for quantum physics and those domains. But no, they actually mean like the URL. Okay, cool, thanks. For each domain, we calculate the percentage of web pages that are collected in the first iteration. Domains where over 10% of the web pages have been collected are classified as math-related. For example, mathoverflow.net. Subsequently, we manually annotate the URLs associated with mathematical content within these identified domains. So mathoverflow.net/questions. Web pages linked to these URLs, yet uncollected, will be added to the seed corpus. This approach enables us to gather more positive examples, thereby training an improved fast text model capable of recalling more mathematical data in the subsequent iteration. Okay, and then they do this for 4 iterations of data collection. We end up with 35.5 mathematical web pages, totaling 120 billion tokens. Cool. In the 4th iteration, we notice that nearly 98% of the data has already been collected in the 3rd iteration. So we cease data collection. Okay, so there is diminishing returns. Yeah, there's no surprise here. I guess for them, the diminishing returns came after number 4. Okay. To avoid benchmark contamination, we follow the following paper to filter out web pages containing questions or answers from English mathematical benchmarks and Chinese benchmarks. The filtering criteria are as follows. You gotta stay hydrated. Are as follows. Any text segment containing a 10-gram string that matches exactly with any substring from the evaluation benchmark is removed. For benchmark texts that are shorter than 10 grams but have at least 3 grams, we employ exact matching to filter out contaminated web pages. Okay, cool. Now, so this was all for collection and decontamination. So now at this point, the team has collected the data. So now how do they validate the quality of the data after collecting 120 billion tokens and decontaminating it? So we run pre-training experiments to investigate how the DeepSeekMath corpus compared with the recently released math training corpora. MathPile, OpenWebMath, and ProofPile 2. I see. So to validate that it is good quality, they just pre-train, they just take, I guess in this case it's 4 different models, right? Or I guess we have 4 architectures that are identical. And if it's pre-trained, then it's random init, random initialization. And then they just go, you know, let me get the pen here as well. Whoops. Hello. All right. So we'll call this 1, 2, 3, and then the DeepSeekMath corpus is 4. So they'll just literally just train it on 1, 2, 3, 4. Okay. This is the DeepSeek model. Training setting. We apply math training to a general pre-trained language model with 1.3 billion parameters, which shares the same framework as the DeepSeek LLMs, denoted as DeepSeek LLM 1.3 billion. We separately train a model on each mathematical corpus for 150 billion tokens. All experiments are conducted using the efficient and lightweight HAI LLM training framework. Following the training practice of DeepSeek LLMs, we use the AtomW optimizer with beta 1 and beta 2 as 0.9, 0.95, with weight decay of 0.1, along with a multi-step learning rate schedule where the learning rate reaches the peak after 2,000 warm-up steps and decreases to 31.6 after 80% of the training process. Further decreases to 10% of the peak after 90%. We set the maximum value of learning rate to 5.3E4 and use a batch size of 4 million tokens with a 4,000 context length. Okay. So this is just kind of about the architecture. And I guess across benchmarks, do they outperform in everything? So they outperform here, 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 here. And then even in... Wait, how'd you get 0%? Is this because it's a Chinese benchmark? Bro, how'd you get 0%? Wait, but no math training had 0.8. Okay, let's go to the evaluation. This is very interesting. I think it's because it's a Chinese benchmark. It's very likely that these are in English, and then maybe this had some multilingual within it. That's like the only thing I could think of. How do you get 0%, dude? What? Okay, evaluation results. The DeepSeekMath corpus is of high quality, covers multilingual mathematical content, and is the largest in size. So yeah, it is also the largest in size, as we see in Table 1. High quality, we evaluate downstream performance on 8, 1, 2, 3, 4, 5, 6, 7, 8. I can count mathematical benchmarks using few-shot chain of thought prompting. In Table 1, yes, in Table 1 there is a clear lead. Multilingual. Okay, so it is because it's multilingual. I was about to say this is hilarious. Just straight 0%. I learned nothing. Yeah, okay, but it's multilingual. So it encompasses so multiple languages, predominantly featuring English and Chinese as the two most represented languages. It enhances mathematical reason in both English and Chinese. In contrast, existing mathematical corpora, which are primarily English-centric, show limited improvement and may even hinder performance in Chinese mathematical reasoning. I mean, okay. Large scale, yes, cool. Large scale, we have a lot more tokens. Okay. Training and evaluating now the base 7 billion model. Okay, so let's check this out. So far, so good. To my one viewer, so far, so good. This paper is quite interesting. Okay, I'm gonna grab more water. Look at that. No spill. No spill, dude. No spill, man. Alright, one sec. Still no spill. Oh shit, it did spill. No, it did spill. That's all good. I deserve it. It did. No, it's because I don't think I closed it properly. Oh well. I got. I deserve it. Alright. Alright, so now let's talk about the base 7 billion model. But I do want water though, come on. Alright. In this section, we introduce the DeepSeekMath base 7 billion, a base model with strong reasoning abilities, especially in mathematics. Our model is initialized with the coder model and is trained for 500 billion tokens. The distribution of the data is as follows. 56% from the DeepSeekMath corpus that they introduce, 4% from algebraic stack, 10% from archive, 20% is from GitHub code, and the 10% is natural language data from Common Crawl in both English and Chinese. Now, I am very interested in what this is, like what that 10% is comprised of. I'll play around with it maybe if I have the time, and then we could kind of prod at it to see like what this 10% is. We mainly adopt the training settings specified in 2.2.1. Are we on? What section am I even on? I'm at 2.3. 2.2.1 was, just this architecture details. Except that we set the maximum value of the learning rate. So they, did they increase it? I think it was 5.3, but it was E minus 5, yeah? Sorry. Oh, it's 5.3 E minus 4 to 4.2. Okay, so they lowered the learning rate and then use a batch size of 10 million tokens as opposed to what they do last time. 4 million. Oh, so, okay. Lowered the learning rate and then increased the batch size. Okay. We conduct a comprehensive assessment of the mathematical capabilities of the base model, focusing on its ability to produce self-contained mathematical solutions without relying on external tools. Yes, because, rely on external tools, but I mean, if you're Google relying on external tools, you get a press conference, so sucks. Solve mathematical problem using tools and conduct formal theorem proving. Beyond mathematics, we also provide a more general profile of the base model, including its performance of natural language understanding, reasoning, and programming skills. Let's go. We evaluate DeepSeekMath base's performance by solving mathematical problems using few-shot chain of thought prompting across 8 benchmarks. These benchmarks encompass quantitative reasoning, and these are all the data sets, and then multiple choice problems covering diverse fields of mathematics from elementary to college level complexity. As shown in Table 2, DeepSeekMath base 7 billion leads in performance across the benchmarks, including the open source base models. Okay. And the recently released Lemma 34 billion. Which underwent math training on Proof Pile 2. Notably, the competition level math dataset, the base model, surpasses existing open source base models by over 10% absolute, which outperformed Minerva 540 billion, a closed sourced base model 77 times larger, which builds on Palm and is further trained on mathematical texts. And here they kind of have all the benchmarks across the board. I guess this is just, it's closed source, so I guess you can't, I guess you can't even call it through API for these data sets. Wait, really? Can you not call Minerva? Is there no API for Minerva? Damn, there's no API on Minerva. All right. So yeah, you just kind of have to take the numbers for granted. But I mean, they ended up comparing it to Gemini Ultra through the API. Mathematical problem solving with tool use. Okay, so this is with the tools, then formal mathematics. Let me just skim through NLU, and then the supervised fine-tuning, and then the reinforcement learning, and then the discussion, and then, okay, cool. So then let's just finish this, and then I will finish the rest of the paper on Wednesday, most likely. So yeah, Minerva, you just gotta take these results for granted. Sucks to suck. So mathematical problem solving with tool use. We evaluate program-aided mathematical reasoning on these data sets using few-shot program of thought prompting. Models are prompted to solve each program by writing a Python program, where libraries such as Math and SymPy can be utilized for intricate computations. The execution of the program is evaluated as the answer. As shown in table 3, this table here, the base model outperforms prior state-of-the-art Lemma 34 billion. Okay. Formal mathematics. Formal proof automation is beneficial to ensure the accuracy and reliability of mathematical proofs and enhance efficiency with increasing attention in recent years. We evaluate the base model on the test of informal to formal proving, which these data sets kind of prefer. So Mistral did outperform these models, the model in MMLU. And then the base coder model outperformed, and then that's interesting. We evaluate on many F to F, a benchmark for formal Olympiad level mathematics. Okay. We use few-shot chain of thought prompting on human eval and MBPP, we evaluate model performance under the 0-shot setting and a few-shot setting, respectively. Where is this cross? Where's this little note? Do I have to really search for it? I really have to search for it, huh? Where is it? Alright, where's the footnote, bro? Come on. No footnote? Or did I just skip it? Evaluation here is the checkpoint right before learning rate decay, which is used to train the base model. Okay, so it's just right here all along. Okay. Natural language understanding, reasoning, and code. We evaluate the model performance of natural language understanding on MMLU, reasoning on BBH, and coding capabilities on human eval. Okay, as shown in table 4 here. Oh, so is this the so Mistral outperforms on language understanding? I assume that's what this column is. DeepSeekMath exhibits significant enhancements in performance in MMLU and BBH compared to its predecessors. So that's how they're going about this. I see. Okay, I guess that's fair. That is fair. So when compared to the network that it was initialized from, and even so, this model before the learning rate decay was used as the initialization for the model, and then I assume this is the complete model all the way through. And across 1, 2, 3, the math base model still outperforms. Still outperforms. Bro, what is happening right now? Yeah, it outperforms. DeepSeek Coder Base illustrating. Oh yeah, so it exhibits significant enhancements compared to its precursor, illustrating the positive impact of math training on language understanding and reasoning. Additionally, by including code tokens for continual training, the base model effectively maintains the performance of the coding base model on the 2 coding benchmarks. Overall, the math-based model significantly outperforms the general model Mistral on the 3 reasoning and coding benchmarks. I guess it's here. This one? Okay. Actually, let's just finish the paper. Supervised fine-tuning. I won't be reading word for word at this point, because I feel like we kind of have a lot covered at this point. So let's see. Supervised fine-tuning, SFT. We construct a mathematical instruction tuning dataset covering English and Chinese problems from different mathematical fields and of varying complexity levels. Problems are paired with solutions in chain of thought and program of thought and a tool integrated reasoning format. Total number of training examples is 776,000. And so they annotate English with tool integrated solutions, adopt a subset of math instruct, along with the training set of Leela OOD, where problems are solved with chain of thought or program of thought. Our English collection covers diverse fields of mathematics, algebra, probability, number theory, calculus, geometry. And then they have the Chinese mathematical data sets, which is K through 12, and 76 subtopics, linear equations, with solutions annotated in both chain of thought and tool integrated reasoning format. So this is, so then I guess when it comes to like college level and above data, I guess really English has the most support. But I think that having Chinese K through 12 is still very good, and still very useful to have, especially for your supervised fine-tuning set. So this is still good regardless. Training and evaluating the Instruct 7 billion. We introduce the Instruct, which undergoes the mathematical instruction tuning based off of the base model. They're randomly concatenated until reaching a maximum context length of 4,000 tokens. Wait, why? Training examples are randomly concatenated. Okay, maybe they'll describe more. I don't understand this, but maybe they'll describe it more. We train the model for 500 steps with a batch size of 256 and a constant learning rate of 5e minus 5. We evaluate the model's mathematical performance, both with and without and with tool use on 4 quantitative reasoning benchmarks in English and Chinese. We benchmark our model against the leading models at the time, closed source models, GPT-4, Gemini Ultra and Pro, Inflection 2, Grok, Baichuan, and the latest GLM-4, and then open source models as well, which is DeepSeek LLM Chat, so their model, Gwen72B, CLLM. Dude, there's so many language models. Like, there's so many language models. I'm going to be honest with you, I don't know half of these language models. I'm going to be completely honest with you. Obviously, I know Mistral. I know Llama. you know, obviously the closed source models have a bunch of hype around them, but like, bro, who's Gwen? I don't know. Oh no, sorry, not Gwen. Quen. I don't know. Sorry to all the Quens in the chat. Sorry, I don't know you. Okay. All right, so this is what they train and evaluate. So they train it on the supervised fine-tuning sets and then compare it to these models, which I assume was this initial table up here, yeah? Oh, the math top 1 accuracy. Okay. Okay, reinforcement learning. So let's talk about the group relative policy optimization. In this section, we introduce our efficient and effective RL algorithm, GRPO. So, PPO is an actor-critic reinforcement learning algorithm that is widely used in the RL fine-tuning stages of LLMs. In particular, it optimizes LLMs by maximizing the following surrogate objective, which is the expectation of Q sampled from the probability of QO sampled from the, I assume, the policy, the old policy models of O given Q. And then we have this objective function here that we have to minimize, where pi O and pi theta old are the current and old policy models. QO are questions and outputs sampled from the question data set and the old policy respectively. Epsilon is a clipping related hyperparameter introduced in PPO for stabilizing trainings. So I guess that's what this whole clipping is for the gradient, it looks like. It could be for the gradient. I don't know. AT is the advantage, which is computed by applying generalized advantage estimation, based on the rewards and a learned value function, V of, I believe that's psi. Thus, in PPO, a value function needs to be trained alongside the policy model, and to mitigate over-optimization of the reward model, the standard approach is to add a per-token KL penalty from the reference model in the reward at each token. As in, like, KL divergence type penalty? Is this what they mean? I wouldn't be surprised. Oh, it's right here. Where R of, is that theta? I don't know. Is the reward model, pi reference is the reference model. Usually the initial supervised fine-tuning model. And then beta is the coefficient for the penalty. But if I recall, but I don't think the, hold on, KL divergence. Yeah, can I just get the equation, please? Yeah, it's the sum pi over log pi. Oh, okay, so I guess they're doing something like that here. So I guess this log ratio, and then, and instead of the probability, instead of it being this times the log, they have this beta penalty term, or this beta weight is the coefficient of the penalty. Okay. I'm not going to pretend like I fully understand this, because I don't. Anyways, as the value function employed in PPO is typically another model of comparable size as the policy model, it brings a substantial memory and computational burden. Additionally, during RL training, the value function is treated as a baseline in the calculation of the advantage for variance reduction. While in the LLM context, usually only the last token is assigned a reward score by the reward model, which may complicate the training of a value function that is accurate at each token. To address this, as shown in figure 4, this one, which we'll look at in a second, we propose group relative policy, GRPO, which obviates the need for additional value function approximation in PPO, and instead uses the average reward of multiple sampled outputs produced in response to the same question as the baseline. Instead uses the average reward of multiple sample outputs produced in response to the same question as the baseline. Okay, I see. So in PPO you have Q, you have the policy model that gives O reference reward value. The reference model and the reward model, there's the KL penalty, or maybe it's the divergence. I assume it's the penalty that gets added to R. So, perhaps then this here, I think it demonstrates this. And then you have the value model, which is V, and then you have, what was this metric called again? Generalized advantage estimation. And then you get A, which then is fed back into the policy model. However, what they propose is to kind of average the outputs here. So instead of getting one output, you kind of average all the outputs from the same question, get the KL term, get the rewards, group computation, and then all the A I assume means it's the action, if I recall correctly, or it's the advantage. Sorry, it's the advantage. More specifically, for each question, GRPO samples a group of outputs from the old policy, then optimizes the policy model by maximizing this objective here. Cool. It seems that this is more or less the same as this is similar to PPO, so nothing too radically different, only they do have so sub I and T, the advantage calculation. So yeah, how do they index this? So from T1 to O sub I, and then I goes from 1 to G, where G is the number of outputs, so the group of outputs. And then what's I? What does I represent? And then this is kind of the penalty term here that they mentioned earlier. So T goes from 1 to OI. What's T? Is this over? Oh, it's just over time? Based on relative rewards inside each group only, which will be detailed in the following subsections. The group relative way that GRPO leverages to calculate the advantage aligns well with the comparative nature of reward models, as reward models are typically trained on data sets of comparison between outputs of the same question. Okay, let's look at this. Let's look at kind of this high-level algorithm. So yeah, the policy model. For each iteration, oh yeah, so it's just the iteration over time, that's T. You get the reference model from the policy model, and then for each step, sample and batch from your task prompts. Sorry. So sample from your task prompts, update the old policy model, sample G outputs for each question in your batch, compute the rewards for each sampled output, and then compute the A is the, oh my god, the advantage. For the teeth token of OI through group relative advantage estimation for GRPO, iteration 1 through mu. And then do they have, oh, these are just hyperparameters. Okay, so mu is just a hyperparameter. Update our fee through continuous training using a replay mechanism, and then do that, and then output the final policy model. And different from the KL penalty term used in 2 that we saw earlier, they estimate the divergence using the unbiased estimator here, which is guaranteed to be positive. Okay. This is a very interesting formulation. Okay. Outcome supervision RL with GRPO. And then process supervision with GRPO, iterative. Okay. Formally, for each question Q, a group of outputs are sampled from the old policy model. Okay. A reward is then used to score the outputs, yielding G rewards correspondingly. Subsequently, these results are normalized by subtracting the group average and dividing by the group standard deviation. Outcome supervision provides the normalized reward at the end of each output and sets the advantages AIT of all tokens in the output as the normalized reward. Then optimizes the policy by maximizing the objective defined in equation 3. Process supervision. Outcome supervision only provides a reward at the end of each output, which isn't sufficient for mathematical tasks. So then they, formally given the question Q and G sampled outputs, process reward model is used to score each step of the outputs, yielding the corresponding results or the corresponding rewards for each output. Then we normalize these rewards with the average and standard deviation. Subsequently, the process supervision calculates the advantage of each token as the sum of the normalized rewards from the following steps, and then optimizes the policy by maximizing the objective in equation 3. Iterative reinforcement learning. As the training progresses, the old reward model may not be sufficient to supervise the current policy model. Okay. Therefore, we explore the iterative RL with GRPO, as shown in algorithm 1, which we kind of went through. In iterative GRPO, we generate new training sets for the reward model based on the sampling results from the policy model and continually train the old reward model using a replay mechanism that incorporates 10% of historical data. Then we set the new reference model as the policy model and continually train the policy with the new reward. Let me reread this part. We generate new training sets based on sampling results and then continually train the old using an old model with a replay mechanism that incorporates 10% of historical data. I assume that this is what happens. I believe. Where's the is the data set, the text prompts, this maintains 10% of historical data? Is this what they mean? I'm not too sure. Okay, training and evaluating. The training data of RL are chain of thought format questions related to GSM-8K and math from the SFT data, which consist of around 144,000 questions. We exclude other SFT questions to investigate the impact of RL on benchmarks that lack data throughout the reinforcement learning phase. We construct the training set of reward models following Wang et al. 2023b. We train our initial reward model based on DeepSeekMath base, so the base model, with a learning rate of 2e-5 For GRPO, we set the learning rate of the policy model as 1e negative 6. The KL coefficient, that beta term that we saw, is 0.04. For each question, we sample 64 outputs. The max length is set to 1024. The training batch is set to 1024. Oh, so this is just kind of dissecting the hyperparameters of everything we read. Table 5 demonstrates the performance of open and closed source models with both chain of thought and tool integrated reasoning. And we will look at that in a second. In this section, we will find our findings in the pre-training and reinforcement learning experience. So let's kind of summarize everything we've learned. Okay. Lessons learned in pre-training. So code training benefits mathematical reasoning. This, I am not surprised. This is table 6. Where's table 5? Oh, it's this table here. Okay, so you have the results. The results are the results. In my opinion, you can have all the empirical data in the world, but the best evaluation metric for large language models is vibes. If I can't vibe with your model, I am deleting it. Plain and simple. It is what it is. But think about it. Think about it. If your model, if you think of your language model as like this assistant, this really cool, super intelligent system, and I can't mess with it and it can't mess with me, the vibes are off. I need good vibes. Okay? It's all about the vibes. That's the best metric. Vibes. But who here has developed a vibe data set? You know, knowing you guys, vibe LLM data set. Video inference for body pose and shape estimation. No, that's not the vibes that I'm thinking of, but that is a vibe. It is a vibe. It is one of the vibes of all time. Where were we? 2-stage training, 1-stage training. Oh yeah, archive papers seem ineffective in improving mathematical reasoning. I mean, I would say it depends. The researchers spent a lot of time really making sure they have a very high quality data set, right? And so I'm willing to bet that if you focus heavily on curating this really potent data set, archive will probably not yield too much benefit. However, if you're just throwing everything at your model, in terms of like pre-training and then fine-tuning on archive, I'm sure that you can get some pretty noticeable improvements. But again, will that improvement in performance from pre-training to fine-tuning yield similar to results as the researchers have gotten? Probably not. They have kind of this unified paradigm that we went through. And then why reinforcement learning works, how to achieve more effective reinforcement learning. Okay. And then this is just kind of the conclusion, limitation, and future work. Yeah, no worries. Okay, so its capability on geometry and theorem proof are relatively weaker than closed models. Cannot handle problems related to triangles and ellipses, which may indicate that data selection bias in pre-training and fine-tuning. Okay, so then, so because they know this, it's very likely that when they redo this curation process that they kind of talked about, then it's very likely that they will kind of heavily, they might shift their efforts in curation for these types of problems. And then the references. Okay.